Okay, here we go. Chapter number 10, review. It's on nuclear for CE chemistry. First up, we need to know the particles. Remember, you've got alpha, which is a 4,2 helium. It has a positive charge. We've got beta, which is 0, -1 E, or you can write it 0, -1 with the B, and it has a negative charge. We have gamma that's very high energy. It's actually known as a ray instead of a particle. It has a 0, 0, but you don't have to write the 0, 0, but it is a ray, very high energy wave, okay? These are the basic ones you need to know. Also, you do need to know a neutron, which is 1, 0, N, a proton, which is 1, 1, P, or 1, 1, H. You do need to know a positron, which is 0, -1 E, or 0, -1 B as a positron. And then just basic nuclear symbol. Remember that a nuclear symbol has a mass number on top. It has the atomic number on the bottom. And then the symbol, whatever the symbol is. Okay? So knowing those generics, we can be able to determine which of those particles, for instance, is the heaviest. Of the particles that we talked about on the last page, the heaviest one is alpha. Okay? As we look at the lightest, we actually have gamma because it doesn't have any rays. Now remember, during some of the lectures that you had before, if we had a positive plate and a negative plate, and we ran alpha, beta, and gamma through that, what would happen? Well, if we had a catch plate over here, as we came through, say that beta was red. Remember, beta is negative, so as it comes through, it's going to actually curve towards the positive side. So here, up here, we would have beta. Say that alpha here is blue. Remember, alpha has a positive charge, so as it comes through, it's actually going to end up down here because it'll be pulled towards the negative plate. Whereas when we do gamma, which has no charge, it's going to go straight through. So we're going to get a gamma that comes straight through like this. So if I ask you what particles and what side do they go to going through a chart, you would know what's going on. Now, so as we have charges on them, alpha and beta are the ones that are going to be charged. Gamma does not have a charge. And forces will affect alpha and beta. Know that we've got several different kinds of nuclear reactions. We have fission, which is, I remember it as falling apart. Okay, if you undergo fission, you've fallen apart. If you undergo fusion, you are putting together to make something bigger. So if I'm fusing something that has been torn, I'm putting it together. You have radioactive decay. Now this can be part of a fission or falling apart, but usually when we talk about fission, it's bigger particles that we end up with. A radioactive decay, we can get off alpha, beta, gamma, protons, neutrons, and it just goes on. Usually smaller particles. Okay, as we're talking about alpha, beta, and gamma, as we look at them, and I'm going to draw them again here. Let's see, I don't remember what color. I think I gave beta red, alpha blue, and gamma green. Okay, if they were to go through different substances, paper, this is my paper, would stop what? Well, it would stop the alpha, but the beta and the gamma would go right through it. So what will stop a beta or a gamma? Well, in your book it said a hand would. We also use 0.5 centimeters of lead. Remember the lead aprons that you wear when you go and get your dentist stuff done? That will stop beta, but gamma goes right through. And that's, we use x-rays, which are gamma emitters, to go through skin so we can see what's underneath it. So what will stop gamma? Well, as you're looking at that, what will stop gamma is 5 feet of concrete or 20 of those lead aprons, making about 10 centimeters of lead. That's what will stop it. So if you were to work around something that was a gamma emitter, you'd want to be in a very specialized wall, either with part lead and concrete or something special about that wall. Okay, when we talk about beta, sometimes we also call beta an electron. This is sort of a misnomer, but we're going to go with it because this is what your book and the test has going on it. So it's capturing electron, would put it on the left-hand side of a reaction. Decay, it would be on the right-hand side. Bombard would be on the left-hand side. So you have to watch the words that they say. Okay, so let's go on. Say that I had polonium, and they gave me 210 polonium. Okay, so what does a 210 mean? Well, I can write it like this, or sometimes you'll see it written as polonium 210. Both ways basically tell me the mass number. They oftentimes will not give you the atomic number because they assume that you know, since it's the element polonium, all you have to do is look on the periodic table, and from the periodic table you can grab that polonium is number 84, and that's what would go on the bottom, is the atomic mass. Now, all I have to do is subtract those two, and I wouldn't write this on the actual paper, but all you have to do is subtract them, and you get the atomic, or the number of neutrons, which in this case would be 166. This would be the neutrons. The number of protons would be 84. Okay, and that would be the number of electrons also. When we're talking about nuclear equations, we're not really worried about electrons in the element itself. We're worried about how the electron or beta particle will affect the nucleus by changing neutron to a proton or a proton to a neutron, depending on what's going on. Okay, so you need to be able to find out how many neutrons and how many protons. You need to be able to say, what's the difference between polonium 210 and, say, polonium 208? Well, it's the number of neutrons. Polonium 208 has 2 less neutrons than polonium 210, so make sure you be able to do that. Be able to write an equation, say that I had polonium 210 and I'm just pulling this out of the sky, so this might actually not work. It's okay, just give you the basic idea. Say that it decayed and I got an alpha particle. What else would I get? So you need to be able to say, oh, 210 is equal to 4 plus what number? 206. 84 is equal to 2 plus what number? 82. Number 82 on the periodic table is lead. So I get lead 206. Be able to write an equation and be able to carry it out. Be able to tell me if I had given you this right here, the lead 206, be able to find what particle it decayed by or was bombarded by. Okay, you also need to know how half-life. Remember that I gave you three equations, it's actually just two, that you could use to find half-life. You can use it by saying initial divided by final is equal to 2 to the n, and big T is equal to T1 half times n. T1 half is half-life. N is the number of half-lives. Big T is total time. And the N is what ties this equation and this equation together. Now, over here, A initial is just initial amount. That means AF is the final amount. And you should be able to take any two things given three things and find any of the others. So say that I had some substance that had a T1 half of 12 hours. Okay, and I started with 30 grams of it. And I want to know after 48 hours how much is left. Okay, so the first thing that I would do is I would take the equation with the big T, and it would be 48 divided by 12 would give me n. Well, that means n would be 4. Then I would take that n over to the first equation, and I would take my 30 grams and divide it by 2 to the 4th to get my amount final. Well, that would be 30 divided by 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, and 1.875 grams is what I would have left, and that would be my answer. Now we should be able to find time. We should be able to do these calculations when the n is not a pretty number, when it's like 4.5 or 3.2. Remember that if I am using the equation AI divided by AF and it equals 2 to the n, and I've got a funky number up here, I need to log both sides. So I take log of this, and over here I take log of this. But it would end up being log of the AI divided by AF equal n log of 2. And then I can go through and solve. Okay, so that's just a little side note. Remember, you need to be able to do that. Okay, when we're talking about the difference between a chemical reaction and a nuclear reaction, remember that chemical involves, the electrons in the outer shell. It does nothing to the nucleus. Nucleus does. It changes the nucleus of an atom. So it changes the number of protons or neutrons, okay, something like that. Okay, when we talk about nuclear energy, like a nuclear power plant, we're talking about fission. So fission is how we get nuclear power. Through a power plant. And you watched several videos on that, so that should be a fairly easy thing. When we talk about radiation sickness can happen because of alpha, beta, and gamma particles all together. Usually, alpha particles don't cause as much radiation sickness, but they can cause radiation sickness because they can be stopped so easily. The problem with substances that are missing some electrons, we call these free radicals. And when free radicals occur because of radiation, they are very dangerous because they're extremely chemically active. In other words, they will react with anything they come in contact with, which is not necessarily good. Okay? They cause some bad things. Remember when we talked about using radiation, for instance, in a diagnostic tracer, diagnostic tracer. Okay, there were some characteristics. You did this actually in your assignment. There were some characteristics that were important. Remember, they were a short half-life, but not too short, because it's got to be long enough to run the test and be able to follow it. It needs to have a non-toxic daughter. Because we want it to be stable after it decays once. And we want it to be fairly available. Okay, we talked about ways that we could read how much radiation is coming off. We had the physical that we read in Curie's and the biological that we read in rads and roentgens and grays. But we want to talk about the medical field, and we want to know the total biological hazard that we have been exposed to. We actually record it in REM. Okay, that's to get our total exposure. Roentgen, rad, and gray give us partial exposures to different types, but to get our total exposure as we're working in a medical field, we would need our REM. Radiation is harmful, remember, to human beings because it creates free radicals, which we talked about on the other side, which are highly reactive. We've been able to create elements. They're known as synthetic elements. Whoops. And these elements, for the most part, are down at the bottom of the periodic table in the F and the lower part of the D. But technetium is also one of the ones that's up higher, number 43. It is a man-made element. So as we go down, especially that bottom row of the periodic table that includes 108 through 118, those are ones we've made, but technetium is also made. Now, how have we made them? We have bombarded another element with either neutrons or betas. We've even used alpha particles and other smaller particles to find new elements. Now, we talk about critical mass. When we have critical mass on an isotope, a radioactive isotope, we're talking about how much material is required, depending on that element, to have a self-sustaining reaction. So when I talk about critical mass, think of self-sustaining radioactive reaction. When I talk about radioactive equations happening in the sun or the stars, those are fusion. So when you're talking about the sun or stars, we're talking about fusion. Okay, and if I'm looking for something that is really, I'm looking at something that's really, really, really old, then I want to make sure that the tracer or the element that I'm looking at, the radioisotope, has a long half-life. Because if it doesn't have a long half-life, it has a short half-life, there won't be enough left in the sample to give me an accurate reading. Okay, I think that's about it. Good luck on the test. Remember, you have a 3x5 card, but only one side, 3" by 5" card, but only one side filled out. And we'll see you at the test.